I'm a huge rocket fan. In fact, I almost worked at SpaceX before deciding to come to Zurich. You have full trust in your system, and then you have the launch day. And after that, everything has to happen autonomously. The rocket is basically on its own. And we believe the drill is very similar. We want to drill to launch, go on a mission, return to the surface intact, can be used right away at the next drill site. And sometimes we call it kind of a moonshot, but into Earth. And honestly, I think it's almost as difficult because the deep Earth has very extreme conditions down there.
Welcome to Geothermal Unleashed, the podcast where we dive into the frontier of geothermal energy and its role in the global energy transition. I'm Elizabeth Cambry with the Valorec New Energies team, and I am here to help spotlight the innovators, technologies, and stories driving geothermal forward. Today, I am thrilled to welcome Jasmin Schoenzart, the founder and CEO of Magnia, all the way from Switzerland. To get our discussion kicked off today, Jasmin, will you introduce yourself and tell us a little bit about your background, education, and career, and how you came to be a part of the geothermal industry?
Hey, Elizabeth. Yes, so nice that you have me on your podcast because I'm actually quite the newbie to geothermal. I'm a chemist by training, and I did my PhD in technology and instrumentation in the US. My route to geothermal is, I think, rather unconventional compared to most people in our community. So I'm a tech developer, meaning I'm working on superconducting magnets and microwave generators called gyrotrons. And what do we do with them is we miniaturize them, meaning we try to keep them very powerful, but make them an order of magnitude smaller. So once we did that, it turned out if you make something very small and very powerful at the same time, they have a lot of new applications. And one of them is geothermal energy, because we can actually put them into a drill string and make a contactless drilling method that will be 20 times faster and 20 times cheaper than anything there is to date.
I love it. Okay, let's talk about the gyrotron. Can you explain how the gyrotron-based drilling system works and how it differs from traditional drilling methods?
Yeah, sure. So the main difference is really that we're aiming for a very high speed, no tripping times, and making it able to go virtually as deep as possible. And how we're doing this by developing a fully contactless method. So there's no bit, there is no wear, there's no tripping times, because we think it has to be a big leap and not just an incremental step like a hybrid method. So that literally means we're kind of launching the drill off the surface like a rocket, which is going into the earth. And then until the mission is complete, the gyrotron drill does not come back to surface. And what is our output? Our microwaves. So kind of like your microwave at home, but like orders of magnitude stronger. And what they can do is they can vaporize rock, any type of rock, really, if it's in close proximity, which is why we're putting the drill underground.
Awesome. Okay, so what are all of the advantages of having the gyrotron downhole rather than keeping it at the surface?
Yeah, so really the most important part is the transmission of the power. So you can imagine the gyrotron as a kind of Yeti-sized bottle device, and the microwaves are coming out of this. The further you go away from the target, the weaker the microwaves will be. So then it does not have enough energy anymore to vaporize the rock if you're too far away. So what are we doing is we put the gyrotron on a drill string, which we're then lowering into the hole. So what we can do with this, it always has the best distance from gyrotron to the rock interface, and we can even adjust this as needed. So by doing this, we can lower the drill 10 kilometers or more. We can do vertical and horizontal drilling because we're kind of in full control of the device, similar to like a mole digging its way downhole. Exactly. So this is the main advantage and the main difference we're making.
Okay, so tell me, how much smaller is the gyrotron compared to other similar units that are on the market today?
So what shall I compare this to? There are two things I can compare this to efficiently, I would say. So the current gyrotrons that are comparable in terms of the output is also a microwave. They're like a large refrigerator or bigger.
Wow.
So this is the device that we shrank into about between a big Yeti-sized bottle and a rather small trash can size. So something that you can actually portably lower into a 30-centimeter borehole.
How did you accomplish this? What were the biggest challenges in trying to miniaturize it?
Yeah, so there are multiple parts to the gyrotron that matter for that question. So the gyrotron has something that's called a superconducting magnet, which is needed to transform power that goes into it to microwaves coming out. So my first step after my PhD was actually to miniaturize the magnet. So they're no longer like a story tall object, but something you can hold in the size of in the palm of your hand. So before this, in the conventional gyrotrons, these were like a meter or two large, kind of cylindrical shaped rings that make the current gyrotrons that big. So obviously, this is nothing that you could ever place down a hole. So making the magnet small was the essential step to believe in the technology to work to then also shrink the surrounding gyrotrons around it. And we're at the point where we understand the physics. We have simulations and models, but there's some engineering work that we still have to do. Hence, we're raising for a seed round now to implement the joint assembly.
Okay, that's exciting. Let's dive in and talk a little bit about the tool design and the materials. So, you have a diamond window. Can you talk about what role that plays in the system and how does it withstand extreme downhole conditions?
Yeah, so for conventional gyrotrons in the laboratory, you do not need a diamond window necessarily. It depends on how much power is coming out or what the gyrotron is experiencing around it. However, our gyrotrons are designed in a way that they are going to deep earth conditions, meaning high pressures, high temperatures. The gyrotron itself is out of metal, so the microwaves cannot transmit through that. So we need something that allows from the generation to let the microwaves out to hit the rock surface. So diamond is one of the strongest materials that we know. So it can it's stable above 700 degrees Celsius, and it can also withstand pressures higher than anything we will encounter. And the good thing about diamond is even if we would exceed 700 degrees C, which would be super, super, super hot rock at this point, there's still even options to make the resistance even better of the diamond. So we think for now, that is the material to go with. We could also throw in sapphire as a different material, but diamond so far is our best choice.
Interesting. Yeah. Okay, so how does the drill create its own casing as it advances downhole, and what are the benefits of forming it's like a glass-lined type of wellbore?
Yeah, so when I got into geothermal and to drilling industry, I spoke to a lot of advisors that are already in oil and gas for decades and that are in drilling for a long time. And what struck out to me rather quickly was that the casing is actually quite the important part of the drilling mission. And luckily, we're able to control our microwaves pretty well. So to give you an example, we can build the device in a way that the ones that come out of the gyrotron straight, let's call it, have a frequency that vaporizes the rock. So kind of it can just go through, make the borehole. We can also add more gyrotrons into the drill string, though, that are pointing left and right. And they can be at a different frequency, which means they're not vaporizing the rock, but they're, in quotes, only melting the rock. And by adjusting this frequency, we can even pretty precisely adjust how thick the casing will be to be stable enough for the borehole conditions down there. So it's kind of an inoperando casing while the drill is descending. That's not just helping with the casing, but also for redundancy. Again, multiple gyrotrons are helpful in case there is a failure from one of the devices.
Got it. So does the overall system experience wear over time, and how does it perform at extreme depths and durations?
So I can only give a hypothetical outlook on that because we haven't actually lowered it into these conditions yet. But the key idea is that it's fully encapsulated, meaning the gyrotron itself is not aware where it actually is. Is it in the laboratory or is it 10 kilometers deep into Earth? Ideally, the gyrotron won't know that because the capsule is shielding the temperatures and the pressures from the device. So the only interaction the gyrotron hopefully has with the rock is that the microwaves go out through the window. So all the cooling and the regulation of, even cooling and pressures inside the capsule should remain stable during the entire mission.
Got it. All right, let's talk about the operational efficiency. Let's go back to this topic. So you mentioned that the gyrotron will eliminate the need or tripping time. So can you explain in more detail how it eliminates tripping time compared to conventional drilling?
Right. So we are building the device in a way that we do not want it to come to the surface until it's done with whatever it was supposed to do. So what does this mean for us? We could build a hybrid system first, that melts the rock a little bit or fracture the rock and then melts it. But we chose to not do that because we think what the drilling industry needs is like the full leap to a fully contactless system that can vaporize the rock quickly. So we want no tripping time at all because if you bring the drill string back up to the surface, this can cause delays and it's very expensive. So there will be a few iterations, of course, on making this device work in the way we're imagining it, but we're aiming for this, again, rocket analogy. Unfortunately, it's coming up a lot. Like it's kind of a launch. You launch the gyrotron drill, and until it's back on launch pad, you hope it fulfilled the mission on the way. So this is definitely the target, which we believe, again, is the only way to make geothermal planetary. It has to be quick, and cheap and fast and ultra deep.
Okay. So how is directional control achieved, and how precise can system be when steering underground?
Yeah, I'd like to use the mole analogy again. If you imagine the animal, it has little feet, so we can do something similar with the gyrotron. We can have multiple of them inside the drill string, and we can switch them on and off since we have control over that. And you can imagine we can switch the left side on or the right side on, and then the drill can turn left or right depending on how we're steering it. Of course, steering is not a very small radius. Like a drill string usually does not experience a super sharp turn. But in this way, we can gradually have it smoothly make turns for eventually building advanced geothermal systems with loops, etc.
Okay. So let's talk now about cost and commercialization of the technology. So how do the economics of this technology compare to conventional drilling, especially considering the upfront R&D investment?
Yeah, so I'm not going to hide it. The upfront R&D is rather high, which on the other hand is very common for deep tech startups. So it's not unexpected, and most people understand that. Luckily, investors have been through that before. We want to be 20 times faster and therefore also 20 times cheaper because we believe people are really into the clean energy and saving our planet, but not if it's an order of magnitude more expensive than other methods that work to bring electricity or energy to us. So yeah, the key is to make it ultra fast and therefore ultra cheap, which is why the R&D already in this early stage targets to make the device as efficient as we want it to be.
I understand. So when do you think you'll have it commercialized?
So between fully commercialized and like pilot projects where potentially some smaller sums of money are floating around, I think we are between 3 to 8, maybe 10 years before the first steam is hopefully being extracted. That being said, it also depends on the location here. So ultimately, we want to make this method work worldwide. So we do not want to target only favorable locations because we think that is not saving geothermal problems globally. But for example, very likely we would start at a favorite hot rock location or a volcano area, maybe Oregon sites or New Zealand. Canada has a few sites like that. So we might do that first to, for example, put a data center for AI. Mm-hmm. Ultimately, we would like to, again, commercialize globally. Therefore, we also have to target rock formations like granite in Switzerland. So until we are like able to do it everywhere, I think we're more like 10 years plus time frame. But we have to start as soon as possible. So it's already kind of too late. We should have started yesterday.
Yeah, I understand. All right, the system has been compared to a rocket. Can you elaborate on that analogy in terms of operation and design?
Yeah, so I'm a huge rocket fan. I guess you can tell from how many times this comes up. In fact, I almost worked at SpaceX before deciding to come to Zurich to incorporate Magnia, so I was quite on the edge there. So a rocket, in my opinion, is such a cool device because what do? You have talented scientists and engineers build it on the ground. You have full trust in your system, and then you have the launch day. And after that, everything has to happen autonomously. The rocket is basically on its own. You can't change anything. You can't change out a certain part. If you have a failure, you have to be able for the system to replace the failure, but not a human actually interacting with the rocket let's say on the outside. And we believe the drill is very similar. So a rocket launches for space, ideally, potentially returns, if it's a SpaceX booster, for example, and similar with the drill. We want the drill to launch, go on a mission, return to the surface intact, can be used right away at the next drill site, ideally. We want the drill to be able to withstand high temperatures and high pressures, also similar to a rocket. And again, we want it to go and we don't want to see it again until it's done. So everything has to be done prior to the microwaves coming out and the gyrotron burrowing itself into the ground. So this is, I think, our rocket analogy. And sometimes we call it kind of a moonshot, but into Earth. And honestly, I think it's almost as difficult because the deep Earth has very extreme conditions down there.
So let's talk about deployment strategy in geology. You've already spoken a little bit about how you want to deploy this technology globally and not be limited by location, but how does geology impact the performance or where you would deploy it?
So I would like to speak from the tech developer point of view, and I'm sure some geologists would disagree with me. But what I can say from the tech point of view is that the microwaves will be able to vaporize any type of rock that we'll encounter simply because we choose the frequency and the energy to be above the threshold of kind of granite. So there's really virtually no limit to what it can vaporize in the regard of the microwave beam coming out. So if I say ideally the geology does not influence our system, this is from the technology point of view. Of course, if you deploy a system globally, there's a lot more that comes with it, like permits, sites, hitting magma down there, or other conditions that change worldwide. So there has to be a lot of extra work in terms of scoping out the right sites, which a lot of people have already done in oil and gas and other drilling companies right now. So we do not think that's actually specific to our technology. So the part that is specific to our technology is how the interaction with the rock is happening. And there I can say from my point of view, the microwaves are strong enough to vaporize any type of rock. So it shall not matter where we are.
That's pretty impressive. Okay. So to conclude today, I would just like to hear more about, I think all of this work is fascinating. I'm extremely impressed by how smart you are and the work that you're doing. It's very exciting. But what are the biggest challenges that you face when you look at everything of trying to deploy this technology?
Yeah, there are a bunch of different categories, I would say, of challenges. Of course, there are technological challenges. And before we chose to kind of come out of the stealth mode and get ourselves out there and be subjected to, critiques, but also like comments, of course, we made sure that everything that we want to do is to our best knowledge and our best educated guess it possible from the point of physics. So there's nothing in our way that we still have to solve that nobody has ever solved before. The key is the integration of the different parts that we have already miniaturized to become one device. And we believe together they can drill where no drill ever has. So there's right now, let's say, except for engineering, I don't want to play the engineering down at all. It's very expensive, needs a lot of capital and time and talented people, but there's no physics standing in our way. And we think that is the most important part when you develop a new technology. Of course, what is challenging, we need to fundraise money, which we have successfully done already in the pre-seed round. Now we're starting our seed round this year. We have a lot of interest from investors, so this is going extremely well. However, the incorporation of like actually having money on site that you can start to pay more people, you can buy materials. This is, of course, also a process that we're going through. And we always feel like we're having a run against time and not necessarily against competitors, but more for our climate, for our planet. We need the solutions soon and we need them fast. So I think that the biggest challenge in our head is like, we want to do these things so fast because we feel like we're already behind and we really kind of owe it to our planet at this point that we find a solution.
I love it. Well, I love all the work you're doing. I'm super impressed. And I want to thank you for joining us on this episode of Geothermal Unleashed. And I hope today's conversation with Jasmin has offered our listeners fresh insights and sparked new ideas about the future of geothermal energy. As we continue to navigate the energy transition, it's clear that geothermal has a powerful role to play, one that's only just beginning to be fully realized. Until next time, keep challenging assumptions, exploring new frontiers, and working together to unlock the full potential of geothermal energy. Thank you.
Thank you.